Okay, so when we left off in the previous video, we were trying to find the eigenvalues, and we kind of rushed through the solution of the problem at the end, so I want to kind of go back and recap what we rushed through. So we're down to a factored polynomial with our lambda plus 3 times our negative lambda squared minus 3 lambda minus 2. And you'll notice that each one of those terms back there has a negative, so let's factor that out completely and have negative lambda plus 3 times lambda squared plus 3 lambda plus 2 equals 0. That second factor should be recognizable as just lambda plus 2 times lambda plus 1. So this is actually negative lambda plus 3 times lambda plus 2 times lambda plus 1 equals 0. And so therefore our eigenvalues are going to be lambda 1 equals negative 1, lambda 2 equals negative 2, and lambda 3 equals negative 3. So now we have to go through and find the corresponding eigenvectors for these. And it's going to be a lot of work because we need to go through and solve our linear system, which is going to be a minus lambda I times v is equal to 0. And for each of these, it's going to correspond to a 3 by 3 linear system. For example, for lambda 1 equals negative 1, we're going to have our matrix A, which is negative 3, 0, 2, 6, 3, negative 12, 2, 2, negative 6. And then subtract away the value of lambda, which is negative 1, and that's going to be times the 3 by 3 identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And this whole thing is times v and equal to the 0 vector. Now, just like before, when you actually subtract a negative 1, that's the same thing as adding a 1. So we're just going to be going through and adding a 1 to the main diagonal of the matrix A. So each of these diagonal entries is going to be increased by 1. So as a result, we're going to have negative 3 plus 1 making a negative 2, but then the 0 and 2 will stay the same. The 6 will stay the same, but now 3 plus 1 will bump that up to a 4. And then we're going to have the negative 12 staying the same. And then the 2's are going to stay the same. And then negative 6 bumped up by 1, of course, is going to make negative 5. And now we have to go through and take this matrix and put this into row-reduced echelon form. And in doing so, you could do this by hand, but we really don't want people to be doing this by hand because of the fact that it's very inefficient and it's very easy to make a mistake with it. So we might as well use our technology with our graphing calculator so that we can go ahead and do this. And it looks like the graphing calculator is hiding, so I will pause. Okay, so I went and picked up my graphing calculator, and there is no nice graphing calculator app for iPads that I'm aware of. If you know of one, let me know. So I'm just going to kind of talk us through how to do this on the graphing calculator. So first thing you want to do is hit the second key in matrix, and you want to go over to edit and choose the size. And again, for this problem, it's a 3 by 3 matrix. We now want to type in the numbers from the matrix, negative 2, 0, 2. And then 6, and then 4, and then negative 12, and then 2, and negative 5. And then once this 3 by 3 matrix is entered in, you hit second and quit. Then you hit second and matrix again, go to math, and choose the row-reduced echelon form, which is on the TI-84 Plus, letter B. And of course, you have to tell it which matrix to use, so you hit second matrix and pull up the matrix A, and then hit enter. Normally, it'll give you a bunch of decimals, so best thing to do is math, frac, convert it into fractions. And the row-reduced echelon form for this one is 1, 0, negative 1, 0, 1, and negative 3 halves. And we have our row of zeros. And again, it cannot be stressed enough that you have to have this row of zeros. If not, we made a mistake. Again, this is times some vector v, which we'll write in components as v1, v2, v3. And this is equal to the 0 vector 0, 0, 0. Now we need to go in and now translate this back. The first row says that 1 times v1 plus 0 times v2 minus 1 times v3 equals 0. That says that v1 and v3 are exactly the same. The second row says that 0 v1 plus 1 times v2 minus 3 halves v3 is equal to 0. That says that v2 is always equal to 3 halves of v3. And it says nothing about v3. So v3 is sometimes referred to as being free in these problems. So now we put this together. We have v1 being replaced with v3. We have the v2 being replaced with 3 halves v3. And v3 is staying the same. If we factor out a v3, we've got 1, 3 halves, and 1. If we now multiply by a 2, we get a more preferred eigenvector of 2, 3, 2. So 2, 3, 2 is the eigenvector corresponding to lambda 1 equals -1. In the next video, we'll go through and find the other two corresponding eigenvectors.